So we should be able to do these parabolas that are pointing up or down, and you should also be able to work with parabolas that are pointing sideways as well. And so it all stems from a formula, and you have to know which formula to use depending on what the shape of your parabola is. Okay, is there anything else we need for this? Important points. I guess we can put the vertex of the parabola here. I don't know if that's important. I think that's about it. Okay. All right, let's go to the next one. This is a hyperbola. And it says to graph it. A good thing to do might be to graph it right away. And hyperbolas might be a little difficult to graph in your graphing calculator. I don't know if the TI-83 or 89 does implicit plots, but this is an example of something that might not look like a function because it wouldn't pass the vertical line test. So whether this is going sideways or up and down, you might have an issue with the graphing of this. Okay, so we have foci at 2, 0, and 2, 4. So 2, 0, and 2, 4 focus points. 1, 2, 2, 3, 4, 2, 0, and 2, 4. Vertices at 2, 1. Put the vertices in purple.
And the vortex is one of the points that gets closest to the director.
Yeah. Okay, closest to the other graph. So this is essentially how your hyperbola is going to look like. Which means the center, put center in quotes, would be this value. This is going to give our shift to the hyperbola. So let's see. Generically, a hyperbola has an x squared over a squared minus y squared over b squared is equal to 1. And the negative might be with the x, the negative might be with the y, and the a and b are other numbers that we have to find. So also, this is kind of generic, and we need to actually change this because there's a shift. And so instead of x squared, it'll be x minus whatever the x component of the new center is. And the center of a parabola is labeled, we didn't label it yet. Oh, okay. So yeah, one of them is negative, one of them is positive, and so we have to know which one is which. And why is y positive and x is negative? Because it's a vertical hyperbola. So we actually need to change the sign to be on the other side. So this is just a generic hyperbola, and with all the shifting and all the different changes in the a's and the b's, and then whether it's going up or sideways, up, down, or side to side, you have to be able to adjust. So it goes up, down. Maybe we can make comments about that. Up, down means that the x is negative. Center If it's not at the origin, that means you're x minus h squared and then y minus k squared. It's not just an x squared and a y squared. It's going to be x minus something squared and then y minus something squared. Okay? So this, by the way, it's called the major axis. X equals 2 is the major axis. And this will help us find our A and B. So I don't know what the formulas are for this. Anybody know? What? Yeah, finding A, B, and C. So A squared plus B squared is equal to C squared. Is that right, or is that for the ellipse? Okay. All right. So we need to know what C is equal to. Or A or B. What do we do from here? Any ideas? Should I look at my notes? Guess I can look at the book.
For hyperbola, it says that cos is plus or minus c equals 0, where c squared is equal to a squared plus b squared.
So
And for c is at plus or minus a equals 0.
focus at plus or minus c comma 0.
Plus or minus c.
Oh. And then the vertex. So this is the generic formula, but since this is for hyperbolas that are going sideways, but since this is looking at the major axis is where A is supposed to be, and since A is since the major axis is vertical, it's perpendicular to or it's not perpendicular, but it's parallel to the y-axis. Our major axis or vertex actually will change a little bit. So our vertex, and we need to do the translation as well. So we're adding 2 to it. So let's see. If you just look at the distance, what's this point? This point is 2, 3, and 2, 1. So this vertex that they're looking at is plus or minus from the middle, and the middle is 2, 2. So we go up 1 and we go down 1, so that's plus and minus 1. Does that part make sense? So not only that, but since this is going up, down, the plus and minus 1 is on the y-axis. The x value is always going to be 2. So that's not changing. So it's the y values that are changing. So if I were to translate this back at the origin, our vertex is along the y at plus and minus 1. It's what?
You're changing the distance to the vertex, but it's to the focus.
Oh, to the focus? Oh, wait, that's C though, right?
What are you doing?
I'm doing the vertex, and then we'll do the focus in a minute. So technically, it's 2, comma, 2 plus and minus 1. If we want to get to the actual vertices. But this is the number A that we're looking for. I'm not using my colors correctly here. So your A is 1, basically. And the A, according to the formula, is what goes under the Y variable. Now, we can't find B, but we can find C, and then that'll help us find B. So let's find C. The focus is plus and minus 2 units away from the middle. And it's going up along the y-axis, since the x is always going to be 2. So this first point, these first points for the focus and the vertex are the unshifted. Now if you shift it at 2, 2, this would be a 2, comma, 2 plus or minus 2. So that gives that 2, comma, 4 and the 2, comma, 0 as the focus points. And that gives us our C value. And then that'll help us find what B is equal to. So B, we got 1 plus B squared is equal to 2. I got square root of 3. Yeah. Oh, yeah. Okay. Better. Thank you. So 1 squared plus B squared is equal to 2 squared. That's where I got my square root of 3. So you can put plus and minus, but that'll automatically come anyways. So that's your B. All right, so our equation then should look like this. Y is first, shifted at 2, divided by the A value that you have, which is 1 squared. And then the X is the one with a minus sign. And then the X value of the center is 2 also. And then this time the number that goes under the 2, under the X is the B value. So it's square root of 3 squared, so I can just put 3 there, is equal to 1. Okay? All right. So there's a lot of formulas that are involved in this, and so it's just a matter of picking the right formula and then being able to use the formula correctly. So remember that when things go sideways, the x and the y switch roles. And so with an ellipse, hyperbola, parabolas, you have to be able to make those adjustments with the x and the y's. All right, let's move on. Let's do number 4. 4C. We have a line and a plane. The line and the plane don't intersect. How would you show that they don't intersect? You dot the plane's normal vector with a direction, so the plane's perpendicular, and the direction vector, if it's parallel to the plane, then that means that vector can be on the plane, and if the vector is on the plane, then it should be perpendicular to the normal. So we need to pull out our directional vector here. 2, 1, 0 plus t times 0, 3, 4. And I hope you guys know how I got that. If you just look at the constants and the coefficients of t, it's like taking this apart, taking this vector apart. And so the direction for the vector is 0, 3, 4. This is the direction of that line. And so if you dot the direction of that line with a normal vector, which is 1, 4, negative 3 for the plane, then if you get 0, then it's perpendicular, then they should not intersect. All right, so the lines don't intersect if you dot D with the normal. What's the distance between the line and the plane? So to find the distance between the line and the plane, I would suggest for you to just pick a point on the plane. So on the line, sorry, pick a point on the line. And that point is 2, 1, 0. That's our starting point for the line. And then find the distance using the distance formula. So the distance formula should be something that you should have in your notes, unless you have it memorized already, in which case you're all good. All right, now we're actually going to do C. It says find the equation of a line that's perpendicular to the plane passing through L. Equation of a line perpendicular to the plane passing through L. So we want an equation of a line. We're looking for an equation of the line. What two things do we need? Need a point in the direction. All right. The line that is perpendicular to the plane. If it's perpendicular to the plane, I think I can get one of these two things. What am I going to get? The normal? Use a normal vector to the plane for my direction, right? So this is the plane, this is the line, and then you have some point over here, 2, 1, 0. You have a direction for the line. You have a normal to the plane. So we want a point perpendicular to the plane. Oops. You have a point perpendicular, you want a line perpendicular to the plane passing through this line. So it looks like I can have a lot of different choices, right? I can make this line pass through this point. I can make that line pass through another point. I can make the line pass through another point. Right? So I just need any point on this line. That would be it. So which point should we choose? The 2, 1, 0 is already given, so let's just use that. And so your new line, let's see, what should we call it? I guess we'll call it little l, or L2. And then the direction vector is 1, 4, -3. So that's our equation of a line. Did it say to write it a certain way? No. Let's write it a certain way anyway. So if we're going to write it, this is in vector form. We can write it in parametric form. 2 plus t, 1 plus 4t, 0 minus 3t. So the x, the y, and the z in parametric form. And then if we want to write it in symmetric form, we just solve for t for each of these. If we solve for t, we're going to get x minus 2. If we solve for t here, we're going to get y minus 1 divided by 4. And if I solve for t here, I'm going to get z divided by -3. Okay? All right, is that good? Okay, let's take a look at some of the other problems on this practice test. Let's just give some hints here. Equation of the tangent line to the curve at a given point. So we need a tangent line. This is x, y, and then they give us a t value. So this is going to be some curve with a t value here. And then what you need to do is you need to find the slope of this line. Now, we actually have a more sophisticated way of finding that equation of a line in 2 dimensions or 3 dimensions. But this is back in Chapter 10, where if you have parametric equations, you can find the slope. And the slope is m is equal to dy dt or dy dx. So we've got dy dx is equal to dy dt divided by dx dt. And then to find the slope, you just get this thing evaluated when t is equal to 1. This is easy enough to eliminate the parameter, yeah, and you'd find dy dx and stuff. And so either way, you can do it. This is asking you to graph this parametric curve, so I'm hoping that you're comfortable enough to use your TI-83 or TI-89, 84, whatever, to be able to graph parametric equations, as well as polar equations. Okay. So without doing it, that's the hint for number 1A, 1B. Set up the integral to find the arc length of this thing. So usually the hardest part about finding the arc length, because you'll have the formula in front of you, the hardest part about finding the arc length is to find the limits of integration. So the A and the B, where it starts and where it stops and starts and stops. And I think the formula is at 1/2 r squared. Oh, that's area. Oh, good thing you have your sheet of notes to use, huh? I can't seem to memorize that. So, for you to be able to find the limits, you should graph it. And graph it, maybe try it from 0 to 2 pi first. And then see if you can use the graphing tool that actually traces it out. So it might overlap and might draw the circle more than once, or whatever this curve is, more than once. So you want to be able to look at those nuances to see where it starts and where it stops. So, say it again? No, when you graph, you're actually graphing. When it says graph it means graph the actual curve. Yeah. So this is a value that you're going to get. Oh, and you should also be able to compute integrals in your calculator and get a decimal approximation, right? Some of these things might be close to impossible to solve by hand, especially arc length that involves square roots. Unless you're really, really, really good and really, really, really fast at doing trig substitutions and things like that, you may just want to punch this in your calculator and get a decimal approximation for your integral. To graph polar, you need to be in polar mode. To find the integral, yeah, you need to be back in the function mode. So integrals in the calculator, make a note of that. Especially if you're doing this in polar coordinates, you're graphing in polar coordinates, and then you have to do the integral. You need to make sure you go back into function mode. Integral approximations. On the calculator. Must be in function mode. Not polar. Okay.
And that's when you type in 0 to pi, 0 to 2 pi.
Yeah. Yeah, you're trying these things as you're graphing it so that you can see. Unless you can look at this and say, oh yeah, that's a cardioid or a limaçon with that's a heart with a hole in it. And if you know that, then you know this is just going to go from 0 to 2 pi. So the trickier ones are if I was asking just for the little piece of the the limaçon on the inside, or if it's a 3 or 4 leaf clover or flower, then if I just want 1 leaf, then you have to make your adjustments with the limits. That's where it gets a little trickier. And this particular problem, I don't know if it's obvious, but to me it's obvious that it goes from 0 to 2 pi. But if you don't know that, then you need to try it. Try 0 to pi, see what you get. Try 0 to pi and see what you get. And if, you know, there's drastic differences in your calculator, then you know you have to pick one that makes sense. Okay? So that's number 1. We did number 2. What's number 3? Vectors. Do we need to do this? We're adding, subtracting, scalar multiplying, finding the angle between them. No. Just might as well. I'm just sitting here killing time anyways. So unit vector in the opposite direction, you divide by magnitude and throw a negative sign in front. So your new vector should be negative vector A divided by the magnitude of the vector. The next one is just addition and scalar multiplication. Here, find an angle between them. Now, there's 2 formulas. I'd prefer you to use the cosine one. I guess I should put, I'm just going to simplify this all the way. Just say theta is equal to the arc cosine of B dot C over the magnitude of B times the magnitude of C. So I may ask you to express your result in degrees, so I hope you know how to convert from radians to degrees. You can have your calculator already set to degrees so that when you press enter here, you're going to get an answer in degrees. Or if you don't want to change from degrees to radians all the time, just get your answer in radians, then multiply by some appropriate factor to make it look like degrees. 180 over pi or pi over 180. Yeah, 180 over pi. Okay, next one, the scalar component projection. So this is our notation for this is COMP. It's a scalar as opposed to PROJ, which is the vector projection. So scalar projection of B onto C. C is the onto vector. And this is B dot C, magnitude of C. And so if you want the actual vector projection, you would multiply this by the unit vector going in a C direction. So that's vector C over the magnitude of C. And that will make this a magnitude of C squared. And then the volume of the parallel pipette spanned by 3 vectors. Whatever. I lost it. Anyways, we have a parallel pipette. We have some 3-dimensional parallelogram. So that's just A dot B cross C. And just for good measure, they tell you to take the absolute value just so it's positive. So that's a formula that should be also in your notes. All these formulas should be in your notes. Yeah, it turns out you could do this in any order that you want. Some orders will give you a negative, some orders will give you a positive, but since you're going to take the absolute value anyways, it doesn't matter. And regardless of what the order is, you're still going to get the same value plus or minus. Okay. So we did number 4. We didn't do all of them, but I gave you enough hints for all of them. Number 5. Oh, yeah, look at that. This one. This is going to be your exam question with the roller, not, this is a helix, but I was going to give you the roller coaster that we had in class. But I decided not to. Give you something else. Anyways, it's going to be the same idea. You have, so this is kind of taking two different types of problems. So I kind of snuck in a TNB problem, that's the Fermat frame, and then a projectile problem. And I kind of put that together in one problem that's connected. And the hard part is that if you don't get the first part right, then you're probably not going to get the second part correct. But I try to find ways to give extra credit depending on how complete or how accurate your answers are. But in general, this projectile problem would have been a problem itself that's broken down into different pieces. And so I just decided to put all this into one big problem. So anyways, the tangent, unit tangent, the unit normal, and the unit binormal vectors, we can find ways to compute those. If they give you a value to put in, I would suggest that you take advantage of that so you're not doing a cross product of functions, but instead you're doing cross products of numbers. That might be a little bit more useful or helpful. So let's maybe try this. So we know that the tangent is going to be the derivative over the magnitude of the derivative. So if we find a derivative of this vector function, we've seen this a bunch of times already. And if we take the magnitude of this, we're going to get a sine squared plus cosine squared plus 1. So that's a square root of 2. And that square root of 2 can go in the denominator. And then we want to put pi over 2 in there. So t evaluate, I'm sorry, not pi over 2, but 2 pi. So we put 2 pi in there. We're going to get sine of 2 pi, which is 0, cosine of 2 pi, which is 1, and then you have this extra constant. And then the last one will be the same. So that's the first one. The second one is the normal vector, which happens to be the derivative of the unit tangent divided by its magnitude. So this is the unit tangent. And fortunately, this 1 over root 2 is constant. So if I want to take the derivative of that, I would leave the constant out by itself and then just take the derivative of the vector. So pieces, I need to do this in pieces. T prime is equal to 1/2 or 1 over root 2, and the derivative, negative cosine t, negative sine t, and 0. 0 is always nice. And the magnitude of this is the magnitude of this vector, sine and cosine and 0 is just going to be 1. So the magnitude is just going to be 1 over root 2. And so if I divide that, that would cancel the 1 over root 2, and then I would just have this. So your normal is just negative cosine t, negative sine t. That's a sine. 0. So cosine of 2 pi is 1, and there's a negative. Sine of 2 pi is 0, and we have a 0. So to find your binormal, instead of dotting your n vector and your t vector, since you're interested in the binormal at 2 pi, you can just dot 0, 1 over root 2, 1 over root 2, dot, cross. So you just cross this vector and this vector, and these vectors are nice numbers already, so that should be hopefully pretty easy to cross. And I'm not going to find b of t, I'm just going to go directly to b of 2 pi, which is the t vector comes first, by the way, yeah? Okay, so you can figure that out. So now the next one, suppose you fly off the roller coaster at t is equal to 2 pi, assume acceleration vector is 0, 0, negative 5. Initial position is going to be r of 2 pi. Now I want to call this r, the initial position, but I don't want to get it confused with this r. I guess it's okay. R of 0, the initial position is r of 2 pi. So this is r. What happens if I put 2 pi into r? What is it? 1, 0, 2 pi. And the initial velocity we'll call v sub 0 is r prime. We took r prime. This is r prime without the 1 over root 2. I mean, it doesn't matter. You can put 1 over root 2 there, but what is it? 0, 1, 1. And so this is again, it's a very simple differential equation where you take the antiderivative twice and then use these initial conditions. So I'll just put dot, dot, dot here. And at some point you have to answer a question based on your results. So after you've found your r position, you look at whether the z value in your r position is equal to 0. Set that equal to 0, and then solve for t, and then put it back in to get your x and your y. Okay? Anything else? So the last one, some fill in the blanks kind of thing. So you should be able to communicate using our vocabulary properly. Yeah.
As long as it's what you say about it, as long as you say everything about it, one thing about it.
As much as you can.
And we're supposed to assume that the roller coaster has no, we're supposed to assume that you're on a space coaster with no gravity.
Well, the gravity is at 0, 0, negative 5. So that's your acceleration. Everything else, you get thrown from your roller coaster And so when you get thrown from your roller coaster, you're that's
So you do want to factor in gravity.
well, the gravity's 0, 0, 5. So that's going to pull you down as you go flying off. If you didn't have any acceleration, then you would have flown in a straight line. It would be similar to that problem that we had some time ago. So at 2 pi, let's say at 2 pi is right here. And you're going along in this speed and in this direction. This is your V naught. This is your R naught. And then as you go flying off this roller coaster, you're going to follow a path, and the gravity is going to pull you down, and then you'll eventually hit the ground somewhere. Okay. All right. Oh, what can be said about the cross product? I don't know. What do you think I'd be looking for that one, for E? Cross product of two two-dimensional vectors. What can you say about it? It's what? It's an area? Area of what? Parallelogram? The magnitude is the area. Point straight out. So if you look at our cross product formula, the cross product formula, if we get it set up, we're putting the two vectors in the second and third rows, right? If you take a look at two two-dimensional vectors, you only have two components for that. So to deal with this, we usually would put 0 in for the third component, and then we would cross it. And when you do cross it, by putting zeros here, right, so there's nothing in the I direction, because if you cross out the I direction, you're going to get 0 minus 0. And there's nothing in the J direction for the same reason, 0 minus 0. So the only thing this will give you is something in the K direction. So your vector is 0I plus 0J plus something K in the K direction only. So I don't know if I would necessarily accept the area idea, but that's true. The magnitude of the cross product will give us the area, but it didn't ask for the magnitude. I was asking for the cross product itself. And this is fairly significant because the cross product is defined for three-dimensional vectors. And if we do a two-dimensional problem, then it's really the result the only result that's meaningful is a scalar, although it's 0, 0 on that scalar. And so that scalar happens to be, in physics it's the torque, but it happens to be the height of the K direction. And this could be either going up or going down depending on which way it's crossed.
So you're suggesting that when we do take this cross product, we're actually you sort of get a 3D result out of a 2D problem.
Yeah, so your problem is a two-dimensional problem, and then your result is all of a sudden in 3D, which is kind of weird. that's how it goes. Not only in 3D, but it's a perpendicular to the XY plane in 3D. All right, so we good? You can view the solutions on that same page. There's pictures and things that might be useful for you to check your answers on. But don't rely solely on this review sheet. I think if you know how to do all the problems in this review sheet, you're well on your way to a C+ or a B- on the test. You have to go beyond that to get a higher grade. I'm just saying. I don't know if that's true or not. It's unsubstantiated.